Hello everyone, let's continue with the proof for insertion sort. So before we do the proof, we first introduce what is the insertion sort. Okay. So basically the insertion sort is a description, algorithm description like this. Of course we know it is a sorting algorithm. And then insertion sort, the input is like you have n numbers in an array A. So start from 1 till n. Okay, same as other sorting problems. So output is like you need to have a sorted sequence A. Okay, still the same sequence, but all the numbers have been sorted. So that's why we write like this. For any number, later will be larger than or equal to the previous, right? AI larger or equal to AI minus 1. So in fact, we want to talk about the idea about the sorting, the insertion sort. So for this one, we go to the book first. So the book, we provide an example for the insertion sort. So the idea is like you play cards, play cards, and then you have some cards in your hand, have some cards on the table, face down, and then you want to, every time you pick up one card, and then insert into a sorted cards on hand, sorted hand. Okay, so this is the basic idea how to do the insertion sort. You will compare from the last one to the front, okay, from back to front, and then compare to find a location where it is larger than the previous but smaller than the next, and then you insert the card in between, larger than or equal to, okay, like this. So for this one, the basic idea is like this, and then we can just give example. For example, if we will perform insertion sort, we'll do like this, because these are the initial cards. Some are maybe face down on the table, some already in the hand. For example, first one you have only one card in the hand, no need to sort because you already sorted. And then you pick up 2 on the table, and you need to insert into a location, whether put it in front of the first one or after the first one. So first card you need to compare with the 2. So compare this one. If this one is larger, so will be on the right. Okay, this new card is larger. If it's smaller, so need to in front. In front, that means because insertion sort card you can find is like the previous one, is the location for 10, now is location for 7. In fact, it's like you move or shift. You move the last or the current one to the right. Okay? So that means current 10. Anyway, this one is larger. So 7 will be inserted in front of it. So 10 will be shifted to the right. So we shifted first. So the same idea for here. So that means we'll shift 5 to the right, just because the 2 will be inserted in front of 5. So 5 will be shifted to the right, and then there's nothing in front, so we can stop the comparison. So we insert the 2 in this available location, and then continue. So that means this is like the shift. So the shaded one is shift, and this solid arrow is the insertion. And then after that we have 2 5, okay, 2 5, and then we have another card picked up, which is 4. So for this 4, we will compare with this one and this one. Okay, 2 and 5. So first compare with 5. 5 is larger, shift it. And then compare with 2. 4 is larger, so no need to shift 2 because 4 will be inserted after 2. Okay, and then we stop. That as long as you can find a smaller one, you stop. Smaller, or you reach the left hand, okay, reach the bottom. So that means 5 will be shifted to the next, and then 5 after 5 shift to next, 4 will be inserted to the place where we put 5. Okay, so this is the sorted array again. So you have 2, 4, 5 before you started the next iteration. So for this one, compare 6 and 5. 6 is bigger, 5 is smaller, so no need to do shift. So you just inserted 6 in the current location, because every time we are just saved the key, or we said this is dark one is the key. That means we want to compare other elements in front with the key. So save this out, and then after that you insert it, because when you shift to the right, that card, that location will be overwritten by another card. So that's the algorithm we need to pay attention to. Okay, so on and so forth. 2, 4, 5, 6, and then next one is 1, and the 1 is smaller than this one, smaller than this one, smaller than this one, smaller than this one. So all of these items will be shifted. Okay, will be shifted. Of course, you can first compare and then shift. You can also compare and shift, compare and shift. So implementation will do accordingly. Okay, so you can just decide. So you have 1, 2, 4, 5, 6, and then last one is 3. So 3 compare with 6, larger. 6 is larger, shift, and 5 is larger, shift, and 4 is larger, shift, and then 2 is smaller. Right? So no need to shift, and then insert the saved one, saved key into the available location. Then you have 1, 2, 3, 4, 5, 6. So you have sorted all of them. So this is the idea for the insertion sort. Okay, insertion sort. So the algorithm is this one. We can go to the slides. So make it bigger. So basic idea is just you will just you need to pick up all the cards on the table. Okay? So from the front, the first one is sorted. So all the cards will be examined, and then from the 2, we'll start from 1, 2 till the end length of the array A. So it's 1, and this one is the length, A dot length. We mentioned before the notation card. This means the size of the array A. Okay. Or we can use this one, doesn't matter, but we prefer this one is more concise, I think. It's conciser. So from 2 to length A, you will examine all the elements, all the cards on the table, and then insert them into in the appropriate location. So how we do that? We first save it out, because I mentioned that you will override that place by another number when we do the shifting. So we need to save it out. So that's the loop contents. In our book, we just ignore the do, but doesn't matter. Okay. So this one might make it more apparent. This is the inside. This is the loop contents. Okay. We first, this one means we do the just like a backup. Okay. You can say it's just a temporary save. So we temporarily save this one into another location. We say it's key. Key is like, in fact, you want to compare with the key. And then next thing is that you need to shift some elements and then insert the key. So we mentioned that you have two methods. You can do one by one every time you compare and then shift, or you can find location and then shift together. So in fact, this one we use the first one. Okay? Every time we shift and then compare with the next one, seems better, okay? Easier. So we do the comparison and the shift. So we find the key here. Okay, we want to insert this one, and then we examine all the elements in front of it. So currently is J, the J's element. Okay, the J's element, and J is also to factor out to get a key. K in fact is just AJ. Okay, we mentioned here. So you will look at all the elements in front of J. Of course, that one, the first one will be J minus 1. So we want to look at one by one from the last one till some elements. Cut till some elements. So we initialize I is the index to examine all the elements in front of AJ, in front of the key. So I initialized to be J minus 1. That's the last element to be examined. In fact, the last element in the array. But when we the last elements in the segment. But in fact, when we do the examination, we do it first, right? Because we from the rear to the front. Okay. So I equal to J minus 1, and then we do a loop. As long this one is like a search, okay, like the search while loop. So that means as long as the element is larger, we'll shift, or as long as we didn't reach the front end, okay, reach the bound. So similar like the search algorithm. So as long as I is larger than 0, means we have not, because we will reduce this I, the index I is here. Okay, this is I. This is J, right? So this is J, this is I, and then this is key. So as long as you minus I, you will not reach the left bound, you will keep minus. So that means we need to make sure I is larger than 0. Larger than 0 means at least it's 1, correct? You can also use larger than or equal to 1, but this is a conciser, correct? So we set I larger than 1. This is for bound checking, correct? Because if we reach the bound, we cannot further do the comparison, and then we need to stop in that location. That means it's already, you have examined all the elements in A which need to be compiled. And then as long as the current element is larger than key, so current is larger, of course key will be inserted in front of it, this one. So AI need to shift to the right, right? So key inserted in front of AI need to shift to right, then you can have an empty space to insert the key. So how to do the shift by one place, okay? You only to shift by one place because you only to reserve one place for the key. And you will shift to the right, okay? Shift to right. So the right one is the next label. Currently you examine AI. You examine AI, and next one will be AI plus 1. So you will shift to this one. Okay. So AI plus 1 will be equal to AI. So don't worry, because if we need to do like this one, means we already shift AI plus 1, right, to the right, or this one is the key. Either is the key or shifted. Okay, shifted. So either is shifted or the key. That means this space can be overwritten. Okay, so that means shift to the right by 1. This is shift. This is do comparison. Okay, iteration. So after shift, this element has been finished. We need to examine the one in front of this one. One more. As long as we didn't reach the bound, we need to keep doing, just like the example. So I minus, this one also is do. If you not do, it's still fine, but you need to use intention. Put this one here. And after you finish all of this search, compile, shift, you have found a location to insert the key. So where is the insertion? So that means this one is a little bit trick there. If we need to, you can find we'll do first I minus, for example, current I is here, and then shift it. Shift it to the right, and then we do I minus 1. I minus 1. We do this one. We found this one is not, current I is I minus 1, is not larger than key, or is already reached the bound. Anyway, this one no need to do anything. So the next one will be the empty element. It's a space which is free, because you shifted before the I before to the right. So this one is empty. AI shift to the AI plus 1. So AI is there. Is there for to be saved. So we have to insert the key into the next, not the current I. Should be I plus 1. You first decrease it by 1, and then no need to do anything for the current AI. Then you can insert the key to the next. So that one will be I plus 1. Okay, so this is the insertion sort. Okay, let's continue for the next one. Loop inferring based proof. First one, we repeat the 3 steps. We have initialization. Statement is true before the first iteration. Maintenance, it is true before and after. And the termination, based on the loop inferent, we decided the last value and then prove the catalyst of algorithm. First one, we need to find the loop inferent. So for here, our main concern is the for loop, because the algorithm in fact is just the for loop itself, and just this one. Other things you just maybe accept the input, or you can just output a sorted array. So the main thing is the for loop. So for this for loop, our main concern is write out the loop inferent. What will be the loop inferent? So that means this loop inferent will be created before we do a loop. That means we haven't done this do. We already have this statement holds. So you need to provide a correct loop inferent. That's called it loop inferent. It means it's not a change. It's not a change during the loops. After finish one loop. So that means we hold true after finish one loop. The loop after, that means finish a loop. This one will hold before, it will hold, or in the beginning. Before means in the beginning of the loop, so on and so forth. That means it will always hold. So what will be always hold? So still go back to the previous example. So in fact, when we do the sorting, we mentioned about it like this one, like playing cards. So you can find here before in fact this one, you don't need to consider, or you can consider you have 4 cards. So you want to insert another one, which is 7. So before you insert, you already have 4 cards sorted, right? So you have, after you insert this 7, you have 5 cards, and then you may have another one which is 6. Before you insert that 6, you have these 5 cards sorted. So this is before we do the insertion. This one seems will be true every time. So this one can be searched, can be used as a loop inferent. But we need to mention, we don't think every loop inferent will be useful for your proof. So you also need to test. Need to test. How to test, I will let you know. So like this one, we want to further explain that question. So before you do the insert 2, you have a sorted number 5. Before you insert 4, you have inserted a subarray. You have already inserted insertion sorting based sorted array, right? 2 and 5, and so on and so forth. You have this one. So every time before you insert a new element into the array, you already have a sorted array. Whether this one will become the selected loop inferent, okay? Loop inferent. It depends whether you can just confirm whether if you proved the maintenance, okay, and initialization and maintenance, and then last step is termination. Whether this inferent will reach the catalyst, because that's the main concern. If we finish all the proof but it still cannot reach the catalyst of the algorithm, then it's useless. So that means we can just confirm this loop inferent will be correct. How to prove this one will be correct? We said after finish all the loop, and then you get a value for the iterator. So you can find this one will be n plus 1, 2, 3, 4, 5 till n, and then you can just do the increase till you get n. N is still less or equal to n. So only after you increase j to be n plus 1, it will exit the for loop. The for loop. So that means you can substitute j. So how to prove? So you substitute j equal to n plus 1 to this one to see whether you can get the things done. So that means at the start of the j plus 1 loop, and then j will be equal to j plus 1, because each is the index j. So j equal to j plus 1, and then you have 1 till j plus 1 minus 1. J equal to n, n plus 1. So this j is equal to n plus 1. The jth loop, j equal to n plus 1, right here. So it's 1 till j n plus 1 minus 1, which is 1 dot n, 1 dot n. So a1 dot n consists of elements originally in a1 till n, still 1 till n, but in sorted order. Done, So that means based on this loop inferent is very promising, because if you finish the proof, this one will reach an answer that all the elements have been sorted. All the elements have been sorted. 1 from 1 to n, a from 1 to n. Consider elements originally in this one, but in sorted order. Okay. So this is the reason. We said we just claim it originally in this one. That means we are doing the sorting of the elements which are in the array A. There's no elements outside of it, because this one the same number. Okay. So this is a good start. That means we choose this one. It's safe to choose this one. It's helpful to. Okay, let's continue with the next steps. That means we have 3 steps. The first one is initialization. Okay, so initialization means before we perform the first step, the loop inferent holds, and then we want to confirm this one. So at the start of the first loop, we said that we must perform the assignment first. Right? So j is equal to 2, and then j less or equal to length of a, and then j plus plus. So that's the 3 steps. Okay? The 3 step for loop. And then we want to confirm when j equal to 2 whether loop inferent holds. So you substitute the j equal to 2. So that means at the start of the first loop, where j is equal to 2, a1 dot j equal to 2, j minus 1 will be 1. a1 is in fact just a1. Correct? a1 tier 1 is only 1. Correct? One element array consists of elements originally in a1, of course, that's correct, but in sorted order, of course, that's correct. No problem, because this is only one element in the array. Of course, it's sorted. Correct? So this one, you write this out. So for here, we just simply write a statement. The inferent trivially holds because A1 is a sorted array. So you can also write like this, but in fact, you can just easy way is that at the start, we need to prove at the start of the first loop, while I is equal to 2. a1 dot dot 2 minus 1, which is equal to a1 tier 1, which is equal to a1. Consider elements originally in a1 but in sorted order. Proved. Okay, so initialization is correct. That means the basis, the foundation of your house is flat. Okay, you can now keep going. So we prove the first step, initialization. Okay, let's continue for the next one. The most important is the maintenance. Right? After we finish the initialization, we need to make sure after finish, before we do the next loop, is correct, and after finish the loop, it's still correct. That's called maintenance. Right? So this one is that first, before we do the first step, it is correct, and then we want to see after finish one loop, it is still correct. So most important thing is that for this one, we need to utilize the loop inferent first, because this is the initial condition you have. Before you do the loop, you already have a sorted array. This sorted array, what's the length? Correct? So you will do like this. So that means at the start of the j's loop, j, this for each 4 means current j, correct? And then you already have a sorted array, which is a from 1 to j minus 1. That means you want to sort aj into a sorted array, which is from 1 to j minus 1, aj minus 1. And the other parts you don't need to care about, because now you are only concern is aj. Others has not been processed, have not been processed. You loop j, j from 2 to the end. Okay, we are only look at aj. So before we do the insertion, do the loop, this is insertion, we already have a sorted array. This is based on the inferent, so you can say by loop inferent, at the start of the j's loop means the j value, not means the second one or third one. That means j equal to j's loop, j equal to j that loop. You already have a sorted array, which is 1 to j minus 1 for the elements coming from a1 to j minus 1. Right? Okay, so that means this is the first statement you want to do. So next one, okay, let's do this. So next one, we want to examine the the loop contents to re-establish the loop inferent. Re-establish means after you finish that loop contents, the loop inferent still holds. Still holds means what? Because if you finish this one, you will go to the next, cut. You finish this one, that means at the start of the j plus 1 loop, the loop inferent holds. J plus 1 means what? A j plus 1, cut. So that one will be, you want to have a sorted array which is 1 to j. You want to have all the elements have been sorted. So that will be the starting position for the next loop, which is j plus 1. So your task is to re-establish the loop inferent after finish the loop content. Okay, let's look at how to prove this one. Okay, so then you need to use logic presented here. Logic, that means what's the things have been done in the loop content. Because without examining this logic, you cannot prove whether you can get a sorted array. Right? Logic means the meaning, what has been done, what operations have been done in this loop. Okay, so in fact for this one, you do the first one is key equal to aj. Okay, this is you just doesn't change the order, so no problem. And then I equal to j minus 1, you will start from this one and then examine all the elements, cut all the elements. As long as it's larger, it will shift to the right, cut, shift to right. And then you insert the key to the ai to the empty location, cut, empty location. So in fact, how many elements you have been shifted to the right? So in fact, you can assume like this one. So cut. So that means you find the location to insert the I to the key. So this is I. This is I plus 1. So you want to insert to this one. You insert all the elements after this one. So including this one, cut. So all the elements from ai plus 1 till aj minus 1, cut. This is aj, this is j minus 1. So I plus 1 and till, that's why we write here ai plus 1 and aj, because this one write like in the order of the shifting. But in fact, you just shift all the elements from I plus 1, this one, till, cut, j minus 1, cut. So because based on this order, you do like this one. As long as it's larger than key, you will shift, and then till you find a one, it is not larger than key or reach the bound. So, but you will do the I minus 1. So that means I is here. So I plus 1 already shift. Okay. So it decreased. Now you need to go back. Okay. So now you have shifted a sorted array, cut. This array is already sorted. You don't change the order. Every time you just sort to the right by one location, cut, if it need to be sorted. So in fact, all the elements just shift to the right by one location. So in fact, these elements will be here, cut, will be here. And then aj, the previous aj, the key, cut, will be here. And then in front is from 1 till I, cut. These are sorted, and this one also sorted, and aj will be larger than all the elements here and less than all the elements here. Of course, this combined together we got a sorted array, cut. This is the idea, because you sort all the elements which are larger than the aj to the right, and then till you write an element ai which is smaller than aj, you stopped, and then insert aj to previous aj value, the key, into the ai plus 1. So of course you combine, you combine a sorted array, and then this element is larger than this order element here, and then another sorted array, this element is less than order element here. Of course you will reach a sorted array which is one more than previous. Previous is from 1 to j minus 1. Now you add one more, so you get a from 1 to j sorted. Okay, so this is the basic idea. Let's look at the words. So, but you can use any words to present this meaning. So by loop inferent, you can say at the start of the j loop, a1 till j minus 1 already have a sorted array containing the elements coming from a1 j minus 1 till j minus 1. Okay? And the inner loop, while loop finds the position I with ai less than less or equal to key. Okay? As long as you find the larger one, you shift. If you find the one which is less or equal to this one, you stop. You insert elements right after that element. So you and also shift all the elements right by one position from I plus 1 till j minus 1. Okay? We mentioned I plus 1 till j minus 1. Then the key formerly known as aj, initially known as aj, is placed in between. Okay? In between. And also we have this condition. This ai plus 1 in fact is just previous aj, or the key. Okay? So this one larger or equal to ai and less than ai plus 1. Of course, then you finish. Okay, you finish. So you can find here we use less or equal to, and then this one is less. The reason is depending on this location, this one, because as long as it's larger than key, you will shift. Okay, larger than the key, ai larger than key, you will shift. If it's equal to the key, you will not shift. Okay, so that's why if you find if equal to this one, so if you have 1 2 2 cut like this one, the 4 will be shift. Initially is 1 2 4, the 4 will be shift, but this 2 will be not shift. Okay, your 2 will be here. So this is depending on this one. So if this one is larger than, this one will be less or equal to. Okay, if you change this one to be equal, then this one will be strictly less than. So on and so forth for this one. Correct? So on and so forth for this one. Okay. And then let's consider. Correct? So that means this one, similar like my previous one, this one only compare the last element of a previous sorted array from 1 to I, and the first element of the third sorted array. Correct? This, or you can say the second or third. So I plus 2, because you shifted this one to the right. Okay? ai plus 1 will shift to ai plus 2. So this one was sorted, this one also sorted, and then this one maintain the sorted order. ai less or equal to ai plus 1, and then less than ai plus 2. Of course, so we combine them together. So this one is by loop inferent. Okay? You can first claim this one, but also you can write after this statement first. By loop inferent, we all have 1 to j minus 1 sorted. But for peace of mind, you can write it first. Later you can use it directly. So you first write by loop inferent, we have this one. This is like the assumption step of the proof by induction. Okay, and then we plus aj is sorted. Okay? a1 till j is sorted. So this means in fact the other part is also sorted. Okay? Other part is also sorted. Okay, so other part is sorted, and then we have the altogether. Okay, we have altogether. We mentioned is the same as this. You have plus one more. Okay, so that means that here j. Now the j is the last element. In fact, this one we may need to write it out in detail, like my previous mentioned. So you shift some elements with a2, a plus 2, a plus 2 tier j, also sorted, and then okay, and then you have you can write this one as I plus I, just I, okay, just I, and then also plus this one. So 1 to I is sorted, and then I plus 2 tier j is sorted, and then also in between we have this order, sorted order. So you combine together, you get a 1 till the end, j sorted. You can also write this one. Initially this one is sorted, and then plus a j is also sorted in the middle, okay, in the middle. We don't know where. So that means initially sorted. This is already based on the by loop inferent, and then you plus aj is also sorted into the sorted array. Then of course we have a bigger, longer sorted array, which is 1 to j. So this one is not very direct, so that's why I prefer like this one. Okay? Like this one I mentioned, you just combine 3 segments and then they're sorted. Okay, this is the most important part, or the difficult part for loop inferent based proof. And for the last one, let's look at, after you have this one, we mentioned it before, in fact you already proved. Okay? We said that when we chose the loop inferent, we confirm this one will reach the proof, the catalyst. So we write it out. So inferent is this one, and then after finish the loop, what will be the conclusion? So it's termination. So we still look at the loop inferent, and then the loop will terminate. So what will be j value? We said it's n plus 1. Okay? Then substitute this one to here, and then to see whether it will prove or not. So the loop terminates j equal to n plus 1. So in fact, I give you a trick. If in a exam, in a homework, even you cannot prove this one. Okay? If you choose a good loop inferent, you do the initialization. For this one, you can leave it empty first. You don't know how to prove it, but you can write the last step. In fact, do not skip this one, because that one will be just not depending on the maintenance. You can just based on the loop inferent to draw the conclusion, okay? To test this step true or not. So yeah, if it's 10 points, this one may be 3 points as well. Maybe the initial one is 2 points, initialization, and this one is 5 points. This one may be 2 points or 3 points. Okay? So that means if it's 3 points, you get it. Okay. So let's look at j equal to n plus 1. That's when the loop was finished. Okay, was finished. And then j equal to n plus 1. You substitute n plus 1 into the loop inferent to see what result you will have. So the inferent states a1 j n plus 1, n plus 1 minus 1, you get n. Consists of elements originally in a, still 1 to n, but in sorted order. Done. Correct? So this is the idea. So you can find here, we just based on this loop inferent, want to reestablish every time when it finish a loop till you finish the last loop, and then exit. Okay, you finish the last loop and then test this one, does not hold. But this loop inferent is at the start of the last loop. Last real loop is, in fact, we haven't done this one. That means when we exit, so that means at start of the last loop, in fact, is just when we exit the loop, the catalyst is still true. Catalyst is still hold. Of course, that's the what we want to have. because at the beginning of the last iteration, in fact, it's just when we exit the loop, the catalyst is still hold. That means after you finish the whole loop, it's still cut. So that means after you exit the loop, it is cut. You exit cut means you have sorted the whole array cut, because this is just what we want to do in the algorithm. The main things of this algorithm is just a for loop. Other things is not important. Okay? Not input output. Okay, not have any impact on the catalyst of algorithm. Okay? Because our main changes are here. Nothing in the front and the end. Okay, hope based on this detailed description you will get a sense of the proof process. So just because we have videos, if you don't have a clear understanding, you can just listen again and then understand, and after that you test, you do some homework. I think you should be able to absorb this knowledge and understand these techniques, and also know how to use these techniques to perform the catalyst proof. So all the related things just involve this algorithm, this technique. That means for proof catalyst. Correct. So what I mean is that we only involve this loop invariant based proof because the most important is the loops. Others you can confirm just manually, right? Okay, this is the thing we want to cover in this slides. Okay, just done cut for this slide. Okay, we'll release this one first and continue with the next one. So next one will be the asymptotic rotation. You can find out we didn't finish the merge sort. That's why we put the deadline for the assignment 1 by the maybe March 1st, okay, maybe like that time. Just because we will go back to the merge sort in chapter 4. Because that one is about in fact in the next merge sort is the next one, but we'll finish the chapter 3 first, and then you can do most of the questions after we finish this chapter 3. But the merge sort part will be need to wait till we finish the next slides. Okay, let's first release the chapter 3, the previous slides videos.